Professor,
Yeah,
would it be okay if I just briefly reminded everyone about SPS, like 30 seconds? At the
sure. Go for it right now.
Oh, right now? Yeah, okay,
Yeah.
cool, sounds good. Hey everyone, my name is Shantanu, rhymes with Canoe, and I'm an officer for the Society of Physics Students. At this point in your undergraduate career, you've probably already heard of SPS, but maybe you're a transfer student, you're just getting started, or you're starting to think about what to do after your bachelor's, or you're looking for research, or you're just someone who wants to have more fun in community during these virtual and unprecedented times. And I just want to remind you that SPS is indeed doing these things and trying to go strong during the virtual semester. Upcoming events include like the first ever inter-UC physics hackathon, faculty student lunches, undergraduate seminars, you name it, we've probably got it. And if we don't, you can help start it. So I just want to remind everyone that that's there if you're looking for any of these opportunities. We also have some general workshops coming up on resumes, etc. So I just want to let you know, I'll put some links in the chat, but that's all I want to say. Thank you so much, Professor Grummy.
Sure. Yeah, guys, you should check out SPS. Thanks. I remember I was in it when I was an undergrad. Okay, folks. So today the plan is to discuss perturbation theory. We're going to continue our discussion of perturbation theory and also talk about degenerate perturbation theory for degenerates. Okay, so let's start by just reminding ourselves where we left off. The idea is we have some Hamiltonian that someone has told us to solve if we want to make some money. And so when we notice that the Hamiltonian has a part that we know and a part that we don't know, and so to solve this, we're going to use perturbation theory. And the main idea of perturbation theory is that I have the known states, known, and then we have the unknown states. This is a picture that I want in your head. That's why I keep drawing it over and over. So these are the known states. I'll draw them as a bunch of energy levels, etc. And this will be the first known eigenstate, the second known eigenstate, the third known eigenstate, etc. And these are the unknown ones that we don't know, we want to know. These are the ones we want. And so that's the first eigenstate, the second eigenstate, the third eigenstate. Oops. And so these are the ones that we want. And so we call these the perturbed states, perturbed states. And we call these the unperturbed states. That's the nomenclature. And the point is that there's a smooth mapping that takes us from the unperturbed state to the perturbed as we turn on the perturbation. That's the picture you should have in your head. You start with the unperturbed, you smoothly turn on the perturbation, and then the unperturbed states smoothly evolve into the perturbed states. That's the picture that works, that has to work for perturbation theory to make sense. And I do want to mention that sometimes it doesn't work, but usually it does. And for this class, it will work for every single situation we look at. And so in this situation, from perturbation theory, we can derive that the nth eigenstate of the perturbed Hamiltonian is approximately equal to the nth eigenstate of the unperturbed Hamiltonian plus the first order correction. And of course, there's all the other higher order corrections, but we will ignore them. And by the same token, the unperturbed eigenenergy is equal to the perturbed eigenenergy is equal to the unperturbed eigenenergy plus the first order correction plus the second order correction plus all the others. And for this class, we're going to ignore all the higher order terms. And so what we've already derived in class is that we derived the first order correction to the eigenenergy is psi n naught, h prime psi n naught. So it's really nice. It's just the expectation value of the perturbation in the using the unperturbed states. For the unperturbed state, the second order eigenenergy correction we have not done yet. We're going to do that today. Not done yet. We'll do that today. And then the first order correction to the eigenstate we did do last time, and we saw that it's equal to this funny sum, which I was trying to explain last time, give you some intuition for that. It's the sum over the unperturbed states, all the unperturbed states except for the nth one, the one that we're talking about. And divide by this, in the denominator, there's an energy. So it's this funny sum, but it's really important. Okay, it's a sum over the unperturbed eigenstates. So each unperturbed eigenstate gives a little bit of itself to the perturbed state. That's the way to think about it. Okay, so now let's do an example. Now it's time for an example. And for the example, what we'll do is my favorite, my favorite thing in quantum mechanics is particle in a box. So I'll take a box, a nice particle in a box of some length, 0 to L. But now I'm going to do something funny to the box. I'm going to put a weird potential inside of it. I'm going to put this weird potential inside of it here, where this is a potential V of x is equal to alpha x minus L over 2 to the cubed third power, where this is L over 2, of course. All right. So that's the situation. And so now what I'm saying is, what are the eigenenergies and what are the eigenstates for this Hamiltonian, for this box?
I got a question about that.
Sure.
Wouldn't this perturbation also decrease the potential to the left of the mark L over 2?
I only put it on half.
Okay.
I mean, I could have put it on the whole thing if I wanted to, but I don't. I only put it on half. So let's do it like this. So V of x is equal to alpha x minus L over 2 cubed for x greater than L over 2 and 0 for x less than L over 2. Okay? So this is like a really weird problem. And so I'm telling you, here's the problem, go solve it. Tell me the eigenstates and the eigenenergies for this problem. And this is actually kind of realistic. I mean, stuff like this really happens in nature all the time. We're often faced with problems just like this. And so now it's time for you to go out and do a real world thing and solve this. And of course, you can't. You look at yourself and you say, well, is this a simple harmonic oscillator? And is it a simple harmonic oscillator? Tell me. Is it a simple harmonic oscillator?
No way.
That's right, because the potential is x cubed. Simple harmonic oscillator goes as x squared. So it's not a simple harmonic oscillator, and since the only thing you know how to solve are simple harmonic oscillators, you're screwed. You don't know what to do, you can't solve it. It's hopelessly hard, and you can't do it. So then you go and you say, well, I know what to do. I'm going to use perturbation theory. And I'm just going to plug into those stupid little formulas that we derived. Rather than trying to solve this numerically on a computer, which is, well, it used to be hard, now it's actually pretty easy, but rather than just doing some numerical simulation, let's actually use perturbation theory. And so to use perturbation theory, then all we got to do is find E n1 and psi n1, because we know that the eigenenergy for this problem is going to be the unperturbed eigenenergies, which we know, plus the first order correction. And I should put wigglies here because it's approximately equal to. And we know that the approximate eigenstates are going to be equal to actually I could turn that off, is going to be equal to the unperturbed eigenstates that we know plus the first order correction. So that's that. So then we're good. That's how we're going to solve it. And so first, let's remind ourselves what are the unperturbed eigenstates, and we know that. And I'll just write down the formula because this is something that you guys all know from last semester. The unperturbed states are going to be just our little internal wave states, right? That we all know and love. And then the unperturbed eigenenergies are just going to be the way I like to remember it is it's h bar squared k squared over 2m for k is equal to n pi over L. And you just plug that into there, and you get the unperturbed particle in a box eigenstates, which are, where's the little formula for it? I don't feel like deriving it. There it is. N squared pi squared h bar squared all over 2 and L squared. All right, is that looking okay? Those are the unperturbed states and eigenenergies. And so now we just, so basically we just plug into the, so basically this is the answer. We're almost done. We just have to calculate these two things. So let's calculate them separately. So let's calculate the first order energy correction. And that's just that formula. Psi n naught h prime psi n naught. So that's an expectation value. So that's an integral. And so that's going to be an integral of psi n naught. So let's do that. It's going to be square root of 2 over L sine n pi over L x. Now we should complex conjugate it, but it's a real function, so we don't have to. Then we have to put something here, and then we have to do the wave function again. Square root of 2 over L sine n pi over Lx. Yeah. Okay, so there's three things missing: that, the bottom, and the top of the integral. So okay, so what goes here? Somebody tell me.
A new v function.
Exactly, it's h prime. That's exactly right, which is going to be that new potential, alpha x minus L over 2 cubed. Good. And so what's the bottom limit of the integration?
Is it L over 2?
That's right. And what's the top limit?
L.
That's right. Why didn't we do 0 to L?
Because
Why?
the potential only starts in the middle, like the perturbation only starts from L over 2.
Exactly. In other words, the perturbation is 0 in that other region. So that part of the integral is 0. Exactly. Good. All right. That's it. I'm not going to do any more for that energy, because once we have a definite integral, I'm going to stop, because the assumption in this class is that definite integrals are just trivial. All right. So that's sort of like our mind frame. So now let's do that.
Professor, should the
Yeah.
H prime part include the momentum, the kinetic energy, or is it just the online?
No, because remember the H naught is equal to kinetic energy plus potential energy. And so H naught is equal to negative H bar square over 2m del squared plus potential energy is 0. That's H naught. See what I'm saying?
Okay, yeah.
Okay. So now let's find the first order correction, psi n1. And we're just going to plug into that formula. I'll remind you the formula again. The formula is a sum over all the states except for the nth state. And we got to take the H prime and we got to take the unperturbed states and calculate these funny matrix elements that I just on the numerator. And then we got to have the energy difference on the denominator, and we're summing over all the other unperturbed states. So let's do that. So now let's just do it. So that means that psi, let's see, whoops. Means that psi n1 of x is equal to, it's going to be the sum. Now I'm going to use I'm going to sum over the index L instead of M, because M is for mass in this problem. You know, we have an M already, so I'm going to use L instead of M. And so then here, I'm going to put the integral on top, and on the bottom, I'm going to have those energies, which we know, here's the little formula for it over here. And so I'm just going to use those. I'm just going to write L, oops. I'm going to write n squared pi squared h bar squared over 2m big L squared minus the ones we're summing over, which is L little l squared pi squared h bar squared all over 2m big L squared. All right, times psi n naught, which is going to be square root of 2 over L sine n pi over Lx. And I just have to find that integral. And the integral is equal to this thing. It's that integral. And so let's just do the integral. So it's going to be integral. I got psi m naught, which is square root of 2 over L sine, oh, but I'm using L instead of M, so it's L pi over big L x. Something goes there. And then I have the n, square root of 2 over L sine n pi over big L x dx. Okay, and what goes in the middle?
H prime.
Exactly. Alpha x minus L over 2 cubed. And what's the bottom part of the integral? The bottom limit?
L by 2.
And the top?
L.
Exactly. That's it. And so then we just calculate that integral. And it goes here. And we're done. We got it. That's the answer. Now, of course, it's an infinite sum, you know, and so you would like, you know, calculate a few terms and hopefully it would converge. But let's not worry about those nuances. Okay. Yeah.
So when you go from the psi m0 on that first line to the root 2 over L sine n pi over Lx, should that be an L pi x or n pi x?
I'm sorry, I don't know which one you're talking about.
Yeah, it's right below where you wrote the word.
Oh, yeah. It looks like I made a mistake there. Thanks. So let's see. This guy, yeah? That's what you're talking about?
Yes. Okay.
Thanks for noticing that.
Awesome.
Okay. Yeah, it's easy to make a notational error when you're doing all these things. Okay, so that's just an example. I just wanted to sort of just, you know, crank out an example. Now it's time to find the second order correction to the energy. So this makes the energy, so now the eigenenergy using perturbation theory, we have the first order correction, which we just did an example, but to make it more precise, we can add the second order correction. And sometimes we do the second order correction and sometimes we don't. And you might be wondering in your head, you know, why would we do one and not the other? Well, you know, I'm sorry, you might be wondering in your head, you know, when should we do the second order correction? And the answer is, it depends. Okay, it depends on the details. And so really out in the real world, you know, when you do this, the time when we most often do the second order correction is when the first order correction equals 0 out in the real world. So if the first order correction is 0, then we very naturally go to the second order correction. But if the first order correction does not equal 0, then typically we ignore the second order correction. That's typical, but not always. Depends on the details. Okay, so let's find the second order correction. So to find the second order correction to the energy, let's go back to the perturbation equations that we derived, and we're going to find this second order. We want to find the second order energy. So remember the perturbation equations, we had the 0th order equation. I'm not going to write them down. I'm not going to write them all down, at least. I'll write down one of them. We have the 0th order correction, the first order correction, and the second order correction. So which one do we use? Tell me. We derived 3 equations for perturbation theory: the 0th order equation, the first order equation, the second order equation. We are now calculating the second order correction to the eigenenergy. Which equation do we use?
We would use the second order equation, the third one.
Exactly, that's right. It's kind of logical, you know, second order, we want the second order term, so we use the second order equation. That's right, perfect. So let's go back to that. Go back to second order equation. And this is it. Let's write it out. I know you don't remember it, but you remember deriving it. And so it looks like this. Is equal. And the cute thing to notice is that the sum of the superscript for each term is always 2. Plus okay, that's the equation. And so now we want to solve this equation. And so we're going to use our little trick that we've already used before. What do you think we're going to do? Can you guess? We want to solve this weird equation. How do we solve it?
Are we going to multiply by a bra on the left hand side?
Exactly. So let's left multiply by bra. Bra, dude, bra, how's it going? By this little bra. By little bra. Okay, there he is. So left multiply by that. And then what we're going to get is this. Let's just do it. Let's just do the algebra, because it's such an important result. I want to do the algebra for this one. Right, yeah. H prime psi n1 is equal to E n naught. I'll pull that one out since it's a constant. Psi n naught psi n2 plus en1 psi n naught psi n1 plus en2 psi n naught psi n naught. Okay, good. And so let's take a look at this. And first, let's notice for this term, this guy can operate backwards. And what's he going to turn into?
Energy eigenvalue.
Exactly, the unperturbed energy eigenvalue, because that's something we know. So this term will be E n naught times psi n naught psi n2. Now this term, there's not much we can do with him, but let's notice this term. What do I notice about this term that I'm circling? What do I notice about him?
It's the same as the first one.
Exactly. So what can I do for those two? Have the same-
Cancel them out.
Exactly. When you have the same thing on both sides, you just cancel it, right? Kaboom, kaboom. That's nice. Now let's look at this term. What can I say about this term?
We already know it from the first equation, from our previous calculations.
Well, we had a discussion about it because this was when we had that complicated Hilbert space discussion, and I was saying that the perturbation causes the eigenstates to rotate in Hilbert space.
Oh, so it's zero since they are orthonormal.
Exactly. So psi n naught and psi n1 are orthonormal because we know that in Hilbert space, if I have psi n naught, then the perturbation causes all the eigenstates to rotate in order to evolve into the new eigenstates. And so they rotate in Hilbert space. So that's psi n1 there. So they're orthonormal. So that means that this guy goes to 0. Okay, and what about this part right here? What's that equal to?
1.
Exactly. And so this equation is not as hard as it looks, because what we see then is we have, what do we have? Yeah, here we basically, it turned into this. En2, the second order correction, is equal to psi n naught psi n1. So it reduced to like a very simple result, although we're not done yet, because now we have to plug in this. And so it's actually a little bit more complicated because that's kind of a complicated object. But let's just plug it in. We know the formula for it. So it's going to be psi n naught h prime hitting psi n1. And we know what psi n1 is. It's the sum over all m not equal to n. Psi m naught h prime psi n naught all over the difference in energy here times psi m naught. All right, just plug in the formula for it, because that's psi n1. Okay, and so now we got to hit the right-hand side with the left-hand side. And so this guy here is going to slide through, and he's going to hit that guy. And so now we can see that En2 is going to be a sum over all m not equal to n. And then I'm going to have this psi m naught h prime psi n naught. And then it slides through and it's going to look like this, psi n naught h prime psi m naught over E n naught minus E m naught. All right, does that look okay? And then you guys know about this because these guys are complex conjugates. So that's what CC stands for, complex conjugates. And so that means that En2 is going to be equal to m not equal to n. What's our favorite way to write it? Psi m naught h prime psi n naught quantity squared all over E n minus E m naught. And there you have it. And so this is a very famous formula. It's another famous formula. And it's a very important formula. And it looks a lot like, it should remind you of, reminds you of the formula for psi n1, which is of course not an accident because psi n1 was part of it, right there. Okay, so that's a kind of a funny thing. So, okay, so this is the second order correction, and once again, it's a weird sum over the unperturbed states. It's a sum over the unperturbed states. And when you first look at it, like all equations in everything, it just doesn't mean anything to you. If you've never seen it before, it's just gobbledygook, all right? But I want to give you a little bit of intuition for how to interpret this equation. And so this is sort of how to think about it. The idea is that we have our unperturbed states. The unperturbed Hamiltonian gives us all of our unperturbed states. And so we have them all. Here they all are. I'm going to draw them all. Here they all are. And so let's take out one of them. So this one is going to be, this is the one we care about, the nth state. But then there's all these other ones. There's the guys on top and the guys below. And the first guy on top is going to be psi n plus 1, e n plus 1. The next guy on top is going to be psi n plus 2, e n plus 2. The next guy, psi n plus 3, e n plus 3. And then there's a whole bunch more. And then the guys below, psi n minus 1, e n minus 1, psi n minus 2, e n minus 2, etc. And then there's the guy we're talking about, which is this guy. He gets a star. And so the way to interpret this formula is that, like usual, normally all the unperturbed eigenstates are separate. They're orthogonal. They're just independent. They're stationary states. You know, they're independent of each other. But now what has happened is we turn on a perturbation, and the perturbation sort of screws everything up. It makes suddenly the states are no longer orthogonal to each other. The old unperturbed states are no longer orthogonal to each other. They start mixing. You get mixing between the states. I'll say mixing. And that means that the energy shifts. And the way to interpret this formula is, the way to think about it is that, I mean, there's many ways to think about it, but I'm going to tell you my personal favorite that I have found most useful in the 35 years that I've been using this formula. The way to think about it is that each of these states is contributing some little bit of energy to this state. It's changing it, and I'll call that, you know, by a different amount. So each of these unperturbed other states is adding a little bit of energy, and the energies are all different. So I should be writing this delta E differently, but I just don't want to. It's just too hard to write it all. So there's like a little delta E, you know, maybe I'll say, you know, I don't know, 1, 2, 3, 4, 5, 6, you know, there's all these, each state is adding a little bit of energy to the state we care about. Now, how much energy, you know, what is delta E? Well, this amount, delta E, and so now I'll say delta E, the state M is giving energy to the state N, is this much. Psi M naught H prime psi N naught all over E N naught minus E M naught. Okay, so that's how much. So actually, maybe I shouldn't have written these little subscripts. I'll erase them all. But this is the subscript that I should have written, M to N. Okay, do you see that? So every state is giving a little bit of energy to the state we're talking about. Now I'm going to ask, now I want you to take a look at this equation, and I'm going to ask you a question. The states on top of the one we care about, what is the sign of the energy that they're given to it? Somebody tell me.
Negative.
The states on top, what is the sign of the energy that they're giving to the state we're talking about?
Negative.
Okay, Is it, who says positive? Who votes for negative?
Me.
Okay, yeah,
Yes.
it's negative. Exactly. Because on top, EM is greater than EN. So on top, delta E is less than 0. So the guys on top, are they pushing the level down in energy or are they raising it up? Simple question, pushing down or raising up?
Pushing down.
Yeah, pushing. These guys are pushing down. And how about the guys underneath? What's the sign of the energy contributed by the guys underneath? Is it positive or negative?
Positive.
That's right, because En is greater than Em, and so delta E is greater than 0, and so they're pushing up. And that's the intuition that I want you to take home with you, because all the states on top are pushing him down. It's sort of like it's like you're underwater and you're feeling the weight of the water on top of you. It's pushing you down, but all the guys underneath are like buoyancy. They're pushing you up. And by the same token, we could reverse the whole argument, and I could say, just use the same reasoning, and I could say, what is the influence of the nth state on all the other guys? I could just reverse the argument, and I could just say, what is the influence of the state we're talking about on all the other states? And so I will actually ask that question. I'm talking about the nth state, and now I'm asking you, what is the influence of the nth state on the states above it via second order perturbation theory? Is it pushing those states up in energy or pulling them down? Which?
Repelling.
Say it again.
Repelling, kind of.
Is it pushing up or pulling down?
Pushing away, I guess.
I said, is it pushing up or pulling down? Up or down? Positive or negative?
Up.
What?
Up.
Up.
That's right, up. Now, if I'm talking about the end state, what is its action on the energy of all the states below it via second order perturbation theory? Is it pulling them up or pushing them down?
Pushing them down.
That's right, exactly. And so this is the phenomena that we call, and I heard somebody say it, this is the origin of a phenomenon called level repulsion. And that's something that you will hear a lot in physics, that you will hear this term. People will say that these states repel. States are repelling each other. There's level repulsion. And that makes no goddamn sense whatsoever. Why would a state repel? It makes no sense. But if you understand second order perturbation theory, then it makes perfect sense, because the second order correction to the energy by second order perturbation theory is always a repelling action. Levels repel. And it's an actual thing. It's real. Out in the real world, people do notice that when you have nearby levels, they tend to repel each other. And so that's a real thing.
Professor?
Yeah.
So we're talking about the energies, right? Like the energies are being quote unquote repelled, not the states themselves.
That's right. That's right.
Okay. So the interpretation of like the states as rotating still holds here? Due to the perturbation?
Yeah. They're rotating in Hilbert space, but it's hard to sort of get an intuition for what that really means. You know, like what is the physical intuition of a rotation in Hilbert space? It's not so simple, but you actually can get additional insight if you think hard about it, because what's really happening is that, you know, eigenstates orthogonalize. And so this action that we're talking about really is due to an additional orthogonalization of the eigenstates, because the perturbed states are trying to orthogonalize. And this is a result of that, but you know, that's getting too much into the details. I just want you to understand, you know, the energy levels are repelling each other.
Okay, thank you.
Okay.
Professor,
Yeah.
I don't really understand the idea of the levels repelling each other, because in this example, we are talking about the unperturbed states contributing energy to the perturbed state, right? But they don't exist simultaneously, right?
You mean because because the unperturbed states are no longer eigenstates? Is that what you mean?
Yeah, they are no longer states of our system since our system has been perturbed.
That's true. That's actually you're absolutely right. But I'm right too. We're both right. So we can all be friends. We're all right. So look, it's just intuition, you know. The thing to remember is this formula, okay? I wrote the formula down. That's the formula. What I'm trying to give to you is intuition. And so the way you should think about it is, I got a bunch of unperturbed states. I turn on the perturbation and suddenly there's mixing and the unperturbed states start giving little bits of themselves to all the other states. And that is sort of what's happening as they rotate in Hilbert space. And so for the second order energy correction, the simplest, it's intuition. I'm trying to give you like a hand waving cartoon picture for you to keep in your head, because most people cannot remember formulas. They can only remember cartoon pictures. So I'm trying to give you that cartoon picture. So the cartoon picture you should remember is that I have unperturbed states. If I'm talking about the nth one, the guys on top give it energy that pushes it down. The guys below give it energy that pushes it up. Why are they giving it energy? It's because of the perturbation, all right? Normally they would not give it energy because they're all, they're eigenstates. But because of the perturbation, they start to give little bits of themselves to that state. That's the way to think about it, okay?
Okay, but we're talking about the unperturbed eigenstates, right?
Yeah, but we're talking about the evolution from the unperturbed.
Yeah, okay, yeah.
In fact,
I understand.
Okay, but I'll just write it again. Like we're talking about this. This is the picture that's why I keep writing this over and over, because the idea is that we have the unperturbed levels and then we have the perturbed levels, and we're evolving one to the other. And so the intuition is like, how do the unperturbed states evolve into the perturbed states? We're trying to gain intuition on that process. Okay.
Yeah, makes sense. Thank you.
Okay. Sorry, can I ask one more follow-up question?
Yeah.
Okay, so when you say that the energy, like in the process of the perturbation, the energy, like the different energy eigenstates above and below the nth state are pushing up or down, is that sort of like trying to restabilize back to a normal, or back to its normal state, or it's like a non-perturbed state? Or like, is there any like insight with like stability or instability in the system in that case?
Yeah. This is the insight. I mean, I don't. Yeah, sure. This is how you could think about it. This is the problem that we're trying to solve. H naught plus H prime psi n is equal to E n psi n. Okay, that's what we're solving. Okay, that's the whole point, is to solve this problem. And so what's happening is, these form an orthonormal basis. And so the idea is that when we turn on the perturbation, the old eigenstates are not orthogonal anymore. And now I turn on the perturbation, and so their energy levels shift, and at the same time they orthogonalize to become the new eigenstates. And it's that process of orthogonalization that's causing all of this. Okay?
That makes sense.
That's the best I can do.
Thank you.
Okay, so now let's look at this formula. Let's just do one last little look at this formula. There's one additional cute thing to notice. Here, there's one more cute thing to notice about this formula. Let's consider, this is H naught, and these are all the unperturbed states. Boom, 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 boom. There's a whole infinity of them. But there's one bottom one. What is the name of the bottom state in the unperturbed basis? What do I call it?
Ground state.
Exactly. That's the ground state. And he has the ground state energy. Okay. And so now I can say, well, what happens when I turn on my perturbation? you know, I have all these levels, and I can say, you know, I have all these, now I have all these perturbed levels, and I can say, what happens to the ground state via second order perturbation theory. And let's just say, let's ignore let's ignore the first order correction. And let's just look at the second order correction. And the second order correction, of course, is our old friend. Psi m naught h prime psi, and now it's the ground state, the unperturbed ground state. And here we have the unperturbed ground state. Okay, so that's our formula. And so without even really looking at the formula, let's just use our new intuition. I'm sitting in the ground state. What is the amount of energy? I have all those states above me, and by second order perturbation theory, they're giving me some energy. Is that energy they give me if I'm the ground state, is it pulling me up or is it pushing me down?
Pushing down.
Pushing you down.
Are any of them pulling up?
No.
Not a single one. So they're all pushing down. So which way does the ground state go via second order perturbation theory?
It should decrease in energy.
That's exactly right. It's always negative. All right, that's a cute little thing to remember, because, you know, if somebody gives you a system, and suppose that somebody gives you a system and they say, here's a perturbation, what happens to the ground state? And you might say, well, okay, let me do first order perturbation theory. Suppose you do first order perturbation theory, and let's just say by symmetry or for some weird reason it's 0. And you're like, huh, that's funny, the first order correction is 0. So then you say, okay, well, now I guess I got to solve the second order correction. And you're like, oh God, it's second order. That means I got to do that sum and all this calculation. But even without doing any calculation, you can actually answer the question, does the perturbation reduce the energy of the ground state or increase the energy of the ground state? Which does it do?
It reduces it.
Exactly. It stabilizes it. It always lowers the energy. So second order perturbation, the second order perturbation correction always lowers the energy of the ground state. Now that does not mean that the perturbation is that does not mean that a perturbation is always lowering the energy of the ground state. Because remember, you still have the first order correction, and that could be positive. That's sometimes positive, sometimes negative. There's no cute rule for the first order correction, but there is a cute rule for the second order correction. So we could say that if the first order correction is 0, then we know that the perturbation is gonna, like 99 out of 100 times, the perturbation is gonna reduce the energy of the ground state. I mean, you still have the higher order corrections, which might lift it back up, but usually they're very small, all right? You know, because the idea is that the energy corrections get smaller and smaller as you go to higher and higher order. Okay, so that's just a cute little thing to notice, and it does pop up every now and then. Okay, so now
can I ask
yeah.
a question about this? So why does like this thing of like, you know, push-in doesn't exist in the first order correction and only exist in second order correction?
Because the first order correction is this psi n naught h prime psi n naught, and so you can just see that this first order correction is an integral, you know, psi n naught of x star h prime psi n naught of x dx, you know, and there's no sign to this integral, right? You know, when you look at that integral, you just notice it has, it might be positive or it might be negative. It depends on h prime.
Oh, okay. I see it now.
Good, excellent.
Thank you.
Okay. This thing is always jumping around on me. Okay. All right, good. So Okay, so now let's talk about degenerate perturbation theory. Degenerate perturbation theory. And this is the picture you should have in your mind for degenerate perturbation theory. The idea is that suppose now I have some H naught, unperturbed Hamiltonian, and it has all these states. Boom, 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 a bunch of states. But then for one of the levels, it has 4 states that are degenerate, and then boom, 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 boom. So let's say it has some mix of, these are non-degenerate levels, and these are degenerate levels. And this is realistic. This actually happens all the time. You know, some levels are degenerate, some are not degenerate. And degenerate, just to remind you, degenerate states have the same energy. That's the definition of degenerate. Degenerate states have the same energy. So far we've been talking about systems where there is no degeneracy, and we have just derived. And so, but now let's consider some degenerate, if there's some, where there's some degeneracy. So let's suppose that this is state 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, etc. Okay, so these are all the states, and you'll notice that state 5, 6, and 7 have the same energy. All the other ones don't. So now let's look at the consequences of this in perturbation theory. So let's remind ourselves of our little formulas that we've derived so far. We have the eigenenergy of the perturbed. So we're going to turn on a perturbation, and then the new eigenenergies are going to look like this. They're going to look like the old eigenenergies plus the first order correction plus the second order correction, where that's going to be psi m naught h prime psi m naught. Let's derive this one. Okay, that's the energy, and I should put these little wigglies here because it's approximate. And we also derived, we know that the eigenstates are approximately equal to the unperturbed eigenstates plus now this formula, psi, the first order correction of a sum over the unperturbed states E n naught minus E m naught. Okay, so that's what we've derived, all right? So if someone gives you some weird Hamiltonian, which is your old Hamiltonian that you know, plus some H prime, some perturbation, then you can immediately write down the energies and the states using perturbation theory. It's a great trick. Everybody loves it. Everybody uses it all the time. But now let's notice now. But now suppose I say to you, find the new energy for state number 6. And I'm saying to you, find the new wave function for state number 6. All right, so I have this list of states, and I say, I want you to find it for state number 6. So you go, okay, I'll just plug into my formula. Okay, and so you do this, and you say, let's find the energy. You say, okay, the energy for state 6 is equal to it's the unperturbed energy for state 6, which I know, it's in that little list, I know it. And I say, okay, plus, and I can take my old state number 6. I got the H prime, and and I can just find this expectation value. That's easy, that's an integral. But then you go and you say, okay, but let's keep going. And let's notice that now I'm gonna sum over all m except for not 6, and I'm gonna do psi m not h prime psi 6 not squared all over e6 naught minus e m naught. Okay, so now we got to do this sum, and so we just plug in all the states into this sum, and I just plug them all in 1 2 3 4 5 6 7 8 9 10. I just do the sum. But I noticed something. What happens, for example, when m equals 7 in this sum? Somebody tell me.
You'll divide by 0.
Right. And you'll notice the same thing happens if I was to try to calculate the eigenstate, because the same thing's going to happen in the first order correction to the eigenstate. Do you see that? You're going to get a divergence. Okay, I want you all to see that. And if it doesn't make sense, you should ask a question, because this is really important. This is why people always talk about non-degenerate perturbation theory, and they separate that from degenerate perturbation theory. That's why we talk about them separately. And that's why we always make such a big deal about degenerate perturbation theory, because you can see that everything we've just talked about for perturbation theory, because, you know, basically everything we've just done is for perturbation theory are these little formulas I just wrote down. These little formulas are the most important results for perturbation theory, and I'll give them 3 stars. But as you'll notice, if we're talking about degenerate states, then when we plug in to the little formulas that we derived and that everybody loves, we all love these little formulas because they're so easy, they don't work, they diverge, they fall apart. So divergence, so the degeneracy leads to divergence. Degeneracy leads to divergence, and that means, and basically divergence means our formulas don't work. Our formulas don't work. And so, but we love our formulas and we want them to work. And so we gotta figure out, so maybe there's a trick we can do to make the formulas work. And you might be able to see that trick just immediately, because suppose you can see that the thing that's messing us up is that when I look at this term and I try to plug in that 7th level, then you see the divergent term looks like this. Psi 7 naught over h prime psi 6 naught over e6 naught minus e7 naught, right? And these states are degenerate. And so that means that this bottom part is equal to what? Say it.
0.
Yes. And so that means that this term goes to infinity, right? Yes. Everyone should be nodding their head. But now let's do a trick. What could I do to this term to make it not go to infinity? Under what condition would this term not go to infinity? Somebody tell me.
If there's the same
If
term
the
in
numerator
the
is also
numerator.
0.
Okay, a couple of people spoke. So if it won't go to 0 if the top term equals what?
0.
Yes. And you guys all know about that, because it's kind of like, you know, the limit of sine x. This is, you know, our favorite example, sine x over x. What's the limit of sine x goes to, as x goes to 0, sine x goes to 0. And as x goes to 0, x goes to 0. And so, but the limit of sine x over x is what? Somebody tell me.
What?
Exactly. So if the top and bottom both go to 0, then the limit of the ratio can be finite and not diverge. And so then we can not worry about it. And so what we got to do is we got to make it so that the top, so that the numerator does not diverge. So must make numerator not diverge. So if we can make that so that this top part, psi m naught h prime psi n naught equals 0, then, so if we can do this, then our perturbation theory works.
Because it doesn't guarantee it doesn't diverge. Right? Maybe.
I know, you're totally right. And so there is some mathematical nuance here, because it depends how fast they go to 0, right? We want the top one to go to 0 faster than the bottom one, or at the same rate. There's some mathematical subtlety here, right? Okay, let's ignore that, all right? Because I'm not really into mathematical subtlety, you know, I find it tedious. And of course, that means that I sometimes get into problems because, you know, mathematical subtlety sometimes is the most important thing, because if you ignore it, then sometimes you get things wrong. But I'm willing to get some things wrong in order to not have to deal with the big headache of mathematical subtlety. So let's just ignore mathematical subtlety. And physicists often ignore mathematical subtlety. It's basically, the idea is let's ignore it until we get into trouble, all right? Because it turns out that in like 99 out of 100 cases, we can ignore that mathematical subtlety and it just works. But there is that 1 out of 100 times when it doesn't work. But we're gonna ignore that. So you raised a good issue, but for this discussion in this class, we're just going to ignore that issue. And I'm going to assume that if the numerator goes to 0, then we're good. All right.
Okay.
Okay. So, but you raised a good issue. Okay. So, okay. So if we can make this term 0, then our perturbation theory is still going to work. And so then life is sweet. So we got to make that term 0. And let's just remind ourselves, it's hard because you can't see everything, unfortunately, but let's remind ourselves, this is the perturbation, this is the situation. We have some non-degenerate states and some degenerate states, and then some non-degenerate states. Now, this term, let's just write ourselves, like let's write the second order expression. Psi m naught h prime psi n naught. Just as an example, e n naught minus e m naught. Okay, is this term going to diverge for any of these degenerate, non-degenerate states? Answer that question, please, somebody.
No.
That's right. It will not diverge because there's no other term that has the same energy. That's the definition of non-degenerate. So do I have, so when I write the so my question to you is, will the perturbation expansion work for those non-degenerate states? Yes or no?
Yes.
That's right. So the fact that there are some degenerate states at other energies does not matter. The perturbation theory still works. Okay, good. So perturbation theory works for these guys. So we don't have, so even though there's some degenerate states, you don't have to worry about them. So pert theory is okay for them. But how about these degenerate guys? Is perturbation theory going to work for them? Is it going to work?
No, it doesn't.
That's right, because we have a divergence here. So the point I want to make is that the divergence only occurs in the degenerate subspace. And so I will use that term a lot, degenerate subspace. Because the way to think about it is that the degenerate states, and this is the way to think about it in your mind, think of them as forming a mini Hilbert space, their own little Hilbert space. Think of the degenerate subspace as a mini Hilbert space. A little vector space. And that's where the problem lies. So it's sort of like the degenerate subspace is like its own little universe, and let's just take that little universe and separate it from all the other states, okay? So it's the degenerate subspace. So let's deal with the degenerate subspace special, because that's where the problem lies. So we got to fix the perturbation theory in the degenerate subspace. And if you think of it like that, then the solution jumps right out at you. You can see the solution, because look, we need this. We need this thing to go to 0. Psi m naught h prime psi n naught. We need it to go to 0. Now, do we need this thing to go to 0? And the way to think about it is, you know, this is a matrix element. This is the matrix element of the perturbation h prime. And the language that people use is that we say that this matrix element is connecting these two states. Connects. And so this matrix element of h prime connecting these two states, do I have to worry about this matrix element connecting states in the degenerate subspace to states outside of the degenerate subspace? Yes or no?
No.
That's right. It doesn't matter, because the energy is different between those states, and so there's no divergence. On the other hand, do I have to worry about these degenerate states connecting to each other inside of the degenerate subspace? Yes or no?
Yes.
Right. I have to worry about this I only have to worry about this inside the degenerate subspace. And so I got to make that matrix element go to 0 inside the degenerate subspace. And inside the degenerate subspace, that means that psi m naught and psi n naught are in the degenerate subspace. So now I ask the question to you, how do I make sure that that matrix element is 0 inside the degenerate subspace? Somebody tell me.
Make the states orthogonal to each other?
Yes. Yeah, but that's right. But it's not quite the full answer, because if h prime hits that state, it might screw up the orthogonalization. So how do I make the states orthogonal to each other such that when h prime hits them, it doesn't mess up the orthogonalization? What do I do?
We take linear combination so that they are also eigenstates of h prime.
That's the answer. You just invented degenerate perturbation theory. That's it. You just invented degenerate perturbation theory. That's all. That's exactly right. So we have to diagonalize. We diagonalize h prime in the degenerate subspace. And then use those eigenstates. And if we use those eigenstates, then the divergent terms go away. That's exactly it. And you might say to yourself, wait a second, the whole point of perturbation theory is to avoid diagonalization, because diagonalizing things is hard. It's always very hard to diagonalize things. And so you might be thinking to yourself, shit, you know, oh no, now I have to diagonalize something. But it's not so bad. Why is it not so bad? Why is it not so bad to diagonalize the degenerate subspace? Why is that not such a bad thing? Somebody tell me.
Because it is only a small subspace of the total vector,
Exactly.
the eigenspace.
Exactly. It's small. The degenerate subspace is small. Like, look at it. You can just see it right here. Look at these lines I drew. They go down to infinity. They go up to infinity. You know, there's typically an infinite number of eigenstates. And if you were to, and the hard problem is to diagonalize all of them at the same time. That's what it means to diagonalize a Hamiltonian. And that's what we're trying to avoid. That's the hard problem. But our perturbation theory only goes bad in the degenerate subspace. And so it's not such a terrible thing to have to diagonalize a degenerate subspace. That's not so bad. We can do that. That's not going to hurt us. That's not going to hurt so badly. So that's what we do. So now what we do is we diagonalize the degenerate subspace, and then we have we find the new states. I'll call them psi and naught with a bar. Okay, that's the new basis, which is diagonalized in the degenerate subspace, diagonalized in degenerate subspace. So many words. It sounds so complicated when you say it, but to do it, it's not complicated. So that means that our perturbation expansion is the same. Our perturbation expansion is the same. But now we write it like this. I have H equals H naught plus H prime, and everything is the same. We want to find the new eigenenergies, which is going to equal to the old eigenenergies plus the first order correction plus the second order correction. And now this is for the diagonalized, the new diagonalized basis, m not equal to n, psi m naught diagonalized h prime psi n naught. This is the new basis diagonalized in the degenerate subspace, e n naught minus e m naught. Notice I don't have to change. Notice I don't have to change this. It's the same because they're degenerate. We're diagonalizing in the degenerate subspace, so the wave functions change, but the energies don't, because the energies remain the same. We're just making new combinations of them. And then, of course, the eigenstates are going to be the unperturbed eigenstates, now that are diagonalized, plus the first order correction to the eigenstates, m not equal to n. It's going to be psi m naught diagonalized in the degenerate subspace, psi n naught. That's what the little bar on top means, diagonalized in the degenerate subspace. E n naught minus E m naught times psi m naught. Okay, and so now I want you to see that these, so now let's look at these terms. Do they diverge? Do they diverge? Do those terms diverge? Yes or no?
No.
That's right, they don't diverge. So that means that our perturbation expansion works. No divergence. Formulas work. And so the way to think about that physically is that nature hates a divergence. And so what nature wants, see, notice this perturbation formula. You see that second order term? That's an energy. And so if the states in the degenerate subspace do not diagonalize themselves, then the energy of the system goes where? To what?
Infinity.
Yes. And so that means that nature wants those degenerate states to do what?
Or diagonalize themselves.
Yes, nature wants it. Nature wants them to diagonalize. And so that's how you should think about it. When you turn on a perturbation, it causes degenerate states to orthogonalize. They diagonalize the perturbation. Because if they don't do that, then the energy would go to infinity. That's sort of the way to think about it. And so nature wants that to happen. And so what that means then is that when we're talking about what is perturbation theory, what is the perturbation doing in the degenerate subspace? It's causing those states to diagonalize themselves via the perturbation. And so what that means then is what we typically do is we diagonalize and we find those states, but then we just stop right here. So we find, so the idea is if the states are degenerate, then we find the eigenstates, then we diagonalize the perturbation in the degenerate subspace, and we plug into the formula this far, and then we stop here. So this is degenerate perturbation theory. Degenerate perturbation theory. Degenerate perturbation theory just means diagonalize your perturbation in the degenerate subspace and plug in here. And so now you see that your eigenstates, your new eigenstates are going to be the eigenstates of the perturbation in the degenerate subspace. And your eigenenergy is just going to be the first order correction. But when you calculate the first order correction, you have to use the eigenstates of the perturbation. And it's basically these are the eigenvalues. So because notice that if I've diagonalized H prime, then this psi n naught H prime psi n naught is just going to be equal to lambda sub n, the eigenvalue. And so you can see that the first order energy correction, En1, is simply equal to the eigenvalue of H prime in the degenerate subspace. And so that is degenerate perturbation theory. It's like the idea is that for non-degenerate states, you just do everything we just did before, but for degenerate states, you have to make sure
that you have that the perturbation is diagonalized in the degenerate subspace. You have to diagonalize it. Does that make sense? It's sort of, so it's actually kind of simple. It's, it's like we're just using the perturbation expansion that we already used, but we're just making sure it does not diverge. That's all. We're just doing whatever we can to make sure it doesn't diverge. And so the next thing to do, of course, is to do an example. I was hoping to do an example today, but I sort of ran out of time. My favorite example is to derive covalent bonding in chemistry, because covalent bonds are, I think, a beautiful example of degenerate perturbation theory. So basically that's kind of all chemistry. Chemistry, it all comes from degenerate perturbation theory. The covalent bond is an example of degenerate perturbation theory. And it's like when they bring two atoms and you get closer and they form a chemical bond. That's a diagonalization of the perturbation in the degenerate subspace of the atomic orbitals. That's what a covalent bond is. It's exactly what we were just talking about. And so maybe I'll do that next time. I was hoping to do it this time, but kind of ran out of time. Okay, I guess that's it. So bye-bye. See you later.
Thank you.
Bye-bye.
Love you. Thanks.
Okay.